the gravity and to respond and give us plant shape. Of course, that influences not only our ability to explore. I can get the image of astronaut Kate Rubins working with this hardware. It's flown several times before. That influences, the answer to that question influences not only exploration missions in terms of going off Earth and supporting NASA's human exploration missions, but also plant shape here on Earth. Plant shape is critical in breeding programs to determine optimal growth for crop productivity in roots and in shoots. So lots of potential applications, both off the Earth and on the Earth.
Thank you, Chris. If you don't mind, for our viewers at home, if you just want to hold it still and look right at that camera, we'll give them a nice shot. And we'll get ready for questions from the audience, if anyone has any. And the first question here.
I'm just curious how you create fractional gravity in a microgravity environment.
Yeah, great question. Do we have the image of Kate Rubins working with the hardware? So basically through a centrifugation system. So we have a cell culture chamber that has two rotors, centrifuge rotors, and these sort of stack, they align along the radius of the rotor at different distances. And the amount of gravity experienced by the plant varies depending on how far it is along that rotor arm. And so as those spin, they spin very slowly, and we can apply a treatment. Our lowest treatment, I think, is down to about 6 1,000ths of a G, all the way up to 1 G to get a good control for Earth response.
Unfortunately, we don't have that picture available, but we can make that available for our folks online if they're still looking for it. Next question in the back here.
Will there also be any investigation into gravity's effect on photosynthesis in plants?
It's a good question. I'm not aware, certainly not on this flight. I know there are some other plant experiments planned for this mission, none of which look directly at photosynthetic productivity. And I'm not aware of any that have. There have been a number of studies. Plant biology has been happening in microgravity in space all the way back from the 70s forward. And so there have been a number of studies that have grown plants seed to seed, completed entire life cycles, both by the US program and by other national programs. Russia in particular, the Soviets grew wheat several times, as did NASA. And so I don't think there's been a close investigation of kind of the subatomic process that happens during photosynthesis. But in terms of just general yield and output, things seem to work without gravity doing photosynthesis.
We have another question in the back.
Yeah, why did you decide to use this particular species of plant? I think you said it was a Arabidopsis, as opposed to any other species of plant, like a vegetable or whatever.
Sure, it's a great question. We work with Arabidopsis, as do probably 1,000 other plant biology labs. It's kind of known as the fruit fly of the plant world. So if you remember your high school biology, fruit flies are sort of a versatile organism. They're easy to grow in the lab, these plants are. Their entire genome is solved. So we have the whole genome sequence. You can go to arabidopsis.org and you can search any gene you want. You can order a mutation, a knockout in that gene, and get it in the lab and see what it does. So it's very handy genetically, all kinds of genetic tools to work with it. Plus, they're really small. And it's in the mustard family, so the seeds, I can pass this around later. You'll see they're very tiny seeds, and so we can fit a lot of them into the experimental setup.
Looks like we have a question online, please.
So Twitter user Ted here asks, would root or other low-lying vegetables respond differently?
That's a good question. Roots and shoots all respond to gravity. They just have different what we call set point angles. So for example, some roots or some stems, for example, prefer to kind of have a trailing growth habit where they kind of spread out along the ground. And those are still sensing gravity, but their set point, the angle of preference for their growth, is just non-vertical. So in most cases, those are not a matter of sensing gravity. They're much more a matter of how they respond.
Great questions. Anything else in the room? How about in the back here?
Hi, since the plants can sense gravity, is there a period of shock that it goes through during the launch and then when it's in microgravity?
That's great. So one of the fortunate things about this hardware, excuse me, is that we get to launch dormant seeds, and they can sit on station for a little while and still germinate fine when water is added. So part of the hardware design involves the injection of water. The hydration event then initiates the experiment. So in our case, no, they're not growing. They're in really suspended animation, so we don't have to deal with that. I think there are limited effects. There's probably some shock effects for those that are launching live plants, but in our case, it's not an issue.
Another question in the room, please.
Do you have any assumptions about what may happen, or have any thoughts?
Yeah, so the question was, do I have any assumptions about what might happen in terms of what the threshold is for gravity sensing? We have some excellent previous experiments in different species that have placed it somewhere in the 0.3 to 0.5 G range. That's sort of where we're expecting to see something, but because we're doing the entire continuum all the way down into the thousandths, we're also in collaboration with GeneLab bringing sample tissue back. So once these grow, they'll be frozen on orbit, brought back, and then a collaborator at Ohio University, Dr. Sarah Wyatt, will be isolating RNA from these to detect, for example, it could be that we see a growth response at 0.3 or 0.4 G, but a gene expression change may be lower than that. And so that would indicate maybe sensing is happening, but just no growth changes later.
All right, I think that's it for questions. Thank you for joining us, Chris. Next, we're going to hear from Andrew Rush. He is the president and CEO of Made in Space. Andrew's no stranger to our What's on Board show, that they've been with us a few times, and you've already heard from them about their experiment today. But tell us about fiber optics.
Great, thanks. I think we're going to start off with a brief intro video.
There's a really interesting question that we asked ourselves since we started Made in Space, which is, might there be something that you can make only in space that you could bring back to Earth and sell?
So we've built a pilot manufacturing facility that will take Z-band glass up into the International Space Station and then robotically and autonomously pull that glass into optical fiber.
The ideal fiber optic cable is one where the outer diameter does not change at all. There's no impurities inside of it, there's no crystals inside of it, and it's all the same material.
If you make Z-band glass fiber in microgravity, it is somewhere on the order of 10 to 100 times lower attenuation than today's traditional silica fiber.
We hope that we'll be offering, products that are manufactured in space within the next year or two. We would not be here today without NASA and without CASIS and without the investment and opening up of the International Space Station. So as was mentioned in that video, this is a payload that is hosted on the International Space Station National Lab, and we're very, very grateful to be chosen and be hosted by them. So what's going on here? So we are manufacturing an optical fiber, an optical glass called Z-band in the persistent microgravity environment that the International Space Station affords. Well, why are we doing this? Well, Z-band is really, really amazing. It has a transmission window that is like 3 times wider than silica glass, which is the glass that you find in sort of traditional optical fiber that underpins a lot of our long-haul telecommunications networks that we use every day. Whether you're wired into the wall or you're using a cell phone, some of the information that you're interacting with probably went through at some point some optical fiber. So having a really wide transmission window lets us actually send more signal down a single piece of fiber, which means bigger pipes, more data, and we all love more data. The other thing that is really interesting here, as you heard mentioned in the video, is that the signal loss that Z-band achieves, depending on wavelength, is 10 to 100 times better than silica's best attenuation. So that, again, is really, really important. And it's important for another reason that we all care about when we are dealing with, dealing with telecommunications, and that's latency. Basically your signal loss in your material is going to dictate how far I can send a signal before I have to reboost it. And in fiber optic telecommunications, we use these things called repeaters in order to reboost the signal periodically. These repeaters, really, really cool pieces of technology. However, they introduce latency into the system because they have to take the signal in, process it, and amplify it up and send it on again. But if I have a fiber like Z-band that has a signal transmission that's like 100 times better than silica fiber, that means I can go like up to 100 times further without a repeater, which means that I can lower the latency of those lines. So broadly, to really emphasize this, why do we care about this? Well, Z-band optical fiber, when it's manufactured in space, is able to achieve is potentially able to achieve the spectrum, this transmission spectrum that we're talking about. When you manufacture it on the ground, it turns out that there's these microcrystals that form in the fiber that ruin the signal transmission. That each one of these little microcrystals, at each domain, you lose like 4% of the light, and that just completely ruins your signal transmission. If you manufacture it in space, manufacture in a microgravity environment, that crystallization is suppressed, and you get really amazing product, which can revolutionize the telecommunication industry, which could provide better fiber lasers, better sensors, lots of different applications. So what we're doing here on this mission is taking the sort of 2-story tall drop tower that we use on the ground that's human operated and to produce fiber, and shrinking that down into a single express track locker, size of a microwave, and making that robotic. So the astronauts will take our payload out of Dragon, install it on station, give it power and data, and we'll do everything else. We'll start the process robotically. It'll clean the fiber up, it'll spool it up, it'll end the process, and once it's done, it won't quite ding like your microwave does, but then we'll take it out, put it back in the Dragon capsule, and ship it home to characterize that fiber and turn it over to customers, which will be a really, really exciting moment. This will be the first time that we've leveraged the space environment to manufacture a product in space that, because it was manufactured there, it's got these amazing properties that are actually useful and commercially viable, we hope, down on the ground. This is really a pilot factory for us. It's going to produce it's really proving out the manufacturing process, proving out the robotic capabilities, so that in future missions on the International Space Station or on other commercial platforms, we can scale this up to be able to service larger customer base. This material that I have right here in my hand is actually some fiber that we manufactured here on the ground. So this is about 200 meters of Z-band fiber that was manufactured on our equipment during testing. And you can see it's like not much material there, but that's about 200 meters of material. The real spools we use on orbit are not 3D printed. They're going to be metal. So that's the kind of broad principle, and we're really excited about this mission and really excited about the broader program as we carry it forward. Thank you.
Questions from the room? Right here.
Oh, hi. So do you already have paying customers for the material, the fiber optic that you're going to be making up there?
So we have a really good channel partner in a company called Thor Labs, which is actually a subject matter expert in the optical glass itself, as well as a nice long list of people that we're in negotiations with.
Hi. How cost effective do you believe Z-band is compared to other material that's already out there?
That's a great question. So Z-band, when you manufacture on the ground, is used in kind of specialty fiber optic applications like fiber lasers and supercontinuum light sources, and it can sell, depending on the configuration, from anywhere from like $150 a meter to like $5,000 or more a meter, which are big numbers. We have done the analysis that once we have this going at scale, like on a scale that can produce a transatlantic line, we can, on a kind of per sort of cents per kilobyte basis, actually be competitive, or in some cases, even more cost effective than silica optical fiber. Now there's a whole program to develop that, to get there, but it's kind of an exciting thing to be able to say, hey, we have a pathway to produce large scale commercial quantities of material in space in a cost effective way.
A question from online, please.
Sure. Twitter user Ted asks, what is the durability of these fibers in comparison to some of the silicone we use today?
That's a really good question. So silica optical fiber, unjacketed, uncoated, is really fragile, just like Z-bland. So in the process of manufacturing any optical fiber, you manufacture the glass and then you coat it to give it physical strength. So this fiber that I'm holding here in my hand is actually really frail because it wasn't coated. But the fiber that will be produced on orbit will be coated and will have that physical strength similar to that of silica fiber.
Any more questions in the room?
How did you come up with the idea that the crystals were caused by gravity and that would be solved by microgravity?
That's a great question. So we didn't come up with the idea. We are so space is a team sport. So we've actually looked at about 20 years of research that NASA and other agencies have performed, that we're studying Z-bland optical fiber. And basically, some folks came up with a hypothesis to say, hey, we think that in microgravity it'll suppress this crystallization. There were parabolic flight experiments that were done that showed in that limited window of microgravity that you get on a parabolic flight that yes, in fact, we are suppressing crystallization. And so we're taking that research and our experience as the only company that's commercially operating manufacturing technologies on the International Space Station, and combining that and moving forward with this payload.
All right, Andrew, that's all the time we have for questions for you. Thank you for joining us. We appreciate it.
Thank you.
Next, we have our final researchers with us tonight. We have Dr. Alessandro Gattoni. He's the principal investigator for Rodent Research 6 at Houston Methodist Research Institute. And joining him, we have Dr. Yaseman Shirazi. She's the mission scientist for Rodent Research 6.
Thank you. So my name is Alessandro Gattoni. I'm a chairman and professor at the Department of Nanomedicine at the Houston Research Methodist Hospital. What we do in my department is developing implantable drug delivery system for the controlled delivery of therapeutics. For pathologies, they are chronic, so therefore requires administration of drugs for a long period of time, ranging from months all the way to years. First image, please. In this image, you can see a number of different implants that we have developed over the years for a number of different type of application, therapeutic application, ranging from cancer to diabetes and to other kind of chronic pathologies. What makes these implants special is, number one, the ability of being transcutaneously refilled. So they are inserted under the skin, for example, in the inner arm, and they release the drug in a constant fashion over a period of time ranging from, again, months to years. Once the drug is completely gone, then instead of explanting them and reimplant a new one, we can reach inside, reload the drug reservoir with more drug, and the implant is good to go for a extended period of time. The second thing that makes this implant special is the nanochannel membrane that we have developed. And the nanochannel membrane is the one that regulates the release of the drug over a period of time. Please, second image. These nanochannel membranes are microfabricated with the same type of technology that you use for make computer chips, and therefore can manufacture in large quantities in parallel with very tight accuracies in the dimension of the channels. We use channels that are very small. We're talking about 2.5 nanometers in size. For you to have an understanding of what 2.5 nanometer means, is about 20,000 times smaller than our hair, or comparable to the molecular size of a protein. So very, very tiny. Why do we need to go to that extreme in manufacturing complexity to use this type of technologies? Well, the reason is because we have realized that if we take channels that they are that small and we use them as a rate limiting membrane, we can achieve a very steady and controlled delivery of the drug outside of an implanted reservoir for a period of time, they're ranging up the way to months and years, without any sort of pumping mechanism on board of our implants. So that makes a very small, very effective implantable delivery system. We are utilizing these implants for a variety of different applications, ranging from HIV pre-exposure prophylaxis, in collaboration with large pharmaceutical companies such as Gilead Sciences, as well as another application ranging from diabetes, obesity, and metabolic syndrome for those in thyromimetic molecule that would combat the disease. But in the context of the Rodent Research 6 experiment, we are using our implant for the delivery of formoterol in collaboration with Novartis, another pharmaceutical company. The idea is that formoterol will help preventing and potentially treating muscle atrophy, which of course, as you all know, is something that may occur in astronauts unless they train during their stay in microgravity. But of course, many people on Earth are affected by muscle atrophy, people that are at bed rest, people that after injuries or debilitating type of pathologies have to stay at bed rest for long period of time, prolonged periods. So therefore, we have the expectation that this implant may one day solve some of these challenges in patients down here on Earth. I have the actual implant that we are using in the context of the Rosen Research experiment, and is right here in my hands. You can see, you cannot see, it's too small. Well, good, let me see if you can see it better this way. Oops, no, too small.
About the size of a Tic Tac, maybe.
That's right. Well, actually, in the picture, you see multiple of them. There are about hundreds of those. So they are very, very tiny and holds enough drugs for treating these mice that we send on the International Space Station for about 2 months. And Dr. Shirazi is going to present to you the project and experiment timeline.
Thank you. If I can get the next slides. So my name is Yasemin Shirazi. I'm the mission scientist for Rodent Research 6, which is actually the 7th mission in the order of the Rodent Research missions. We've been following the shuttle tradition of not going in order. If I can get the next picture. So why do we want to do this science in rodents? We all know that animal models are valuable translational models for the research that has been done. And next picture, please. And then rodents specifically will provide us extensive experimentation and applying techniques that we typically cannot do in humans. In addition, we all have different backgrounds, genetically, lifestyle and all that, but the rodents are all similar. So we're only looking at one variable, in this case for model, as Dr. Grattoni mentioned. Next image, please. So these are basically 3 of our main hardware. On the left side, you see the rodent habitat. In the middle, you see the rodent transporter. That is the hardware that the mice are currently in. So we load the mice in the transporter about 24 hours before launch. So that was earlier this morning. And then on the right, you see the animal access unit that can be attached to either of those hardware to transfer the mice. And if I can get the next slide. So this is the rodent habitat up close. The mice, this is where the mice will reside during the mission. This has video capability, so we watch the mice daily for a couple of hours to make sure they are eating, drinking, and having a healthy stay on ISS. This also provides air circulation, filter capability, and food and water to the mice for duration of the mission. Next image, please. And then as you can see, we're not up there to do all these experiments. Here we usually have a large group of people to do all the science experiments for us. So we have to rely on our talented crew members. So we have people on our team who train the crew. And then on the left side, you see the microgravity science box, the glove box. And then on the right, you can see our hardware. The access unit is attached to it, and that's how the crew members will retrieve the mice. They take them to the MSG or the glove box to do any type of procedure on them. And next image. So when we do experiments here on Earth, we have the luxury of big spaces, big labs, all kinds of equipment, microscopes, and all that. But on ISS, we don't have that luxury. So this is where rodent research is very unique in the capability that we can do all the research in the glove box. Next slide, please. And this is the space we have to work with. So this is where rodent comes into play to help to work with principal investigators such as Alessandro and his team and take their science from the lab bench to ISS and perform it on ISS. Also, the goal of rodent research is to maximize science return. So with each mission, we harvest thousands of samples, and then they're all archived in the life sciences library at NASA Ames. So each mission sets the foundation for many other research experiments. And then with each mission, we've developed capabilities with the procedures that we do with the hardware. And then if I can get the next slide. So for the last couple missions, we've been able to return the animals live. So what you see is the Dragon capsule that has splashed down into the ocean. The SpaceX team retrieves the capsule. We'll meet them at Long Beach Pier, and then we get the mice back, make sure they're all healthy, and then return them to the scientists so that they can continue their experimentation. And again, I just wanted to mention that rodent research team is a large multidisciplinary team. So we've got scientists, engineers, a large team of mission integration and operations, and I'm just here representing. It's a large team who's been working for a couple months now, and some of them are still at work, making sure we can turn over the hardware and the mice to SpaceX for tomorrow's launch.
All right, with that, we'll take questions for our researchers. Right here in the front row, please.
Hey, how many mice are going to go up tomorrow?
For this mission, we're sending 40 mice, so each transporter can house 20 mice, 10 on each side. And then, as I mentioned, we have the live return capability. So of the 40 that are launched, 20 of them will come back live after 30 days, and then the rest will stay on ISS longer for up to 60 days.
Another question in the back here?
Yeah, I have two questions. The first one is, are the devices implanted here on Earth before they go up?
Yes, we've been doing that in the lab for the last few days. So the science team will load the implants with the treatment or the vehicle, and then there is a very small non-invasive surgery to put the implant under the skin for the mice.
Okay, and my second question is, someone made the comment that space is a team sport.
Exactly.
And we heard that Boeing has a glucose monitor implant also going up in this. Are you going to collaborate in any way from what you are learning in the applications and share information between agencies?
Potential in the future. Both of these, I mean, the glucose monitoring device is a new capability, so I'm sure before we know it, there's another mission going up. There's nothing in work right now, but I'm sure all the scientists in the field will work on that.
And I wanted to add that this experiment, of course, involves a very large number of investigators, not just on the research side and on the NASA side, of course, but also with Novartis. Novartis is putting in substantial resources also for the analysis of tissues and samples, including funding. So it's really, really a broad investigation.
All right, I know we have a question online.
Twitter user Briley here is asking, how long will the mice actually stay on the ISS? What's their duration up there?
For up to 60 days for this mission, and like I said, half of them will come back after 30 days, and then the other half will stay for an entire 60 days.
Up front here.
How do the mice react to microgravity, aside from the medical experiment? I mean,
it's like anyone else who goes to microgravity, like the astronauts. It takes them a couple of days to get used to floating. But then after about 3 or 4 days, you don't even notice that they're in microgravity. They're ambulating normally, running around, eating, drinking. Yeah.
All right, that's going to be it for our presenters today. So thank you both. Appreciate it. And thank you all for joining us live today. As a reminder, please tune in for our launch coverage. Launch is targeted for December 12th at 11:46 a.m. Eastern. We're going to start our coverage on NASA television at 11:15. For more information about this mission itself, please check out www.nasa.gov/SpaceX or www.nasa.gov/station. Thank you all for joining us, and have a great day.
From NASA's Kennedy Space Center in Florida, you're watching live coverage of the 13th SpaceX cargo resupply mission to the International Space Station. Hi, I'm Stephanie Martin, and thanks for joining us. Today's launch to the station is scheduled for 10:36 a.m. Eastern from Space Launch Complex 40 on Cape Canaveral Air Force Station. Coming up, you'll hear about the exciting research heading to the station and get a sneak peek on the events happening here at Kennedy Space Center in 2018. Today's launch will be the first of the year from Pad 40. The Dragon spacecraft and Falcon 9 rocket at the launch pad both previously flew on cargo resupply missions for NASA. At the time of launch, the space station will be flying 258 miles above northern Oman at the southeast tip of the Saudi Peninsula. The Cargo Dragon spacecraft will deliver about 4,800 pounds of science, research, crew supplies, and hardware to the orbiting laboratory. Today's launch has an instantaneous window, which means SpaceX has a single second to launch. About 10 minutes after launch, Dragon reaches its preliminary orbit. It will then deploy its solar arrays and begin a series of thruster firings as it heads to the space station for its targeted arrival on Sunday, December 17th. We're about 34 minutes from today's launch. NASA's Joshua Finch and Mike Curie are monitoring SpaceX's countdown activities in the control center. Guys, how are things progressing for today's launch?
Hey, thank you very much, Stephanie. Good morning, Josh.
Good morning, Mike. Things are progressing toward liftoff of the SpaceX Falcon 9 rocket. Everything's from our position is going well at the moment. Today's will be the first launch from Space Launch Complex 40 since 2016. Mike, can you tell us more?
Yeah, in a recent interview on Pad Status, SpaceX said that they looked at this not only as an opportunity to rebuild the pad after they had an anomaly, but also to modernize it and make it high-tech. The pad, originally built in the 1960s for the Titan rocket fleet, was leased by SpaceX in 2007. The company then made initial upgrades to Space Launch Complex 40 to accommodate the Falcon 9 rocket.
The recent upgrades started with stripping the pad down and adding reinforcements to streamline operations. Some of the pad enhancements include a new transporter erector, augmenting the water systems to add a water-cooled flame diverter, and upgrading the liquid oxygen system.
And with the completion of this pad, SpaceX now has the capability to launch from 2 locations on Florida's Space Coast, Launch Complex 39A at Kennedy Space Center, and here at Cape Canaveral Air Force Station, Space Launch Complex 40.
The countdown has progressed per the timeline. The milestones already performed include collision avoidance coordination with the Eastern Range, a checkout of the Flight Autonomous Termination System, loading of RP-1 began as planned. The Eastern Range confirms it is go for the launch and landing of the Falcon 9 first stage at Cape Canaveral Air Force Station Landing Zone 1, and the loading of liquid oxygen began at T-minus 35 minutes at 10:01 a.m.
And weather today does not appear to be a concern for us. U.S. Air Force 45th Weather Squadron Officer Lieutenant David Myers, our launch weather officer today, briefed the team earlier and says that we can expect winds 9 to 12 miles an hour from the south-southwest, temperature 67 degrees at the time of launch. The only concern that he mentioned was the thick cloud rule, which does not appear to be a concern, even though officially the forecast still says 10% probability of violation. He briefed the team that he is expecting no launch commit criteria violations this morning, so that's good news. And for now, that is our status from Falcon Launch Control. And Stephanie, we will hand it back to you.
Thanks, guys. SpaceX will deliver more than 4,800 pounds of supplies and payloads, including critical materials to support dozens of the more than 250 science and research investigations that will occur during Expeditions 54 and 55. The approximately 26-foot tall Dragon trunk will carry about 1,400 pounds of unpressurized cargo to the station, which means the cargo inside the trunk will be exposed to the vacuum of space, unlike the experiments inside the Dragon that are pressurized with air to simulate the atmosphere. The Dragon spacecraft will spend approximately 1 month attached to the space station and then will return to Earth filled with 3,600 pounds of research, hardware, and crew supplies. Research conducted aboard the International Space Station helps advance scientific knowledge in Earth, space, physical, and biological sciences for the benefit of people living on our home planet. It also serves as the world's leading laboratory where cutting-edge research and technology development is pushing us further toward human deep space exploration missions back to the moon and onto Mars. Our Amanda Griffin recently learned more about an investigation that could help scientists better treat patients with osteoporosis and heal broken bones.
I'm here with Brian Hess, the founder and CEO of Launchpad Medical.
Brian, I understand you're working on a new bone material that we're sending to space. Can you tell us a little bit about how what you're working on is different than what's currently on the market?
Sure. What's currently on the market are bone grafts, and these materials are non-load bearing. They don't have much structural strength, despite being able to regenerate new bone. Our material is actually a bone adhesive, so it's injectable, and when placed in the body, it can actually glue broken bones back together. We get immediate and very strong load-bearing strength when we actually test our material.
So why are we sending this to space?
So what we want to do is we ultimately want to treat patients with poor quality bone. And in space, it's in microgravity, and astronauts are losing up to 2% of their bone mass per month. So it creates a really nice environment to actually test our material. And if we can show that new bone can grow in the presence of our material in space, it potentially could have huge value for us here on Earth for patients with, say, osteoporosis.
Right. Can you tell us a little bit about how your experiment's going to work?
Sure. Our experiment will look at how well new bone grows up in space in the microgravity conditions, but we'll actually compare it to wells which do not have our material as a control, but also to other materials that are currently on the market to see how well we compare to them as a benchmark.
How much growth are we expecting?
What we're generally looking at are the cells and actually how active they are and if they differentiate and proliferate in the presence of our material. And then the biologists back on Earth, they'll be collecting samples of the media and they'll be looking at what's actually produced by these cells. The experiment will be about 14 days, and then we'll do the post-analysis after it returns to Earth.
Excellent.
Thank you.
Back to you, Stephanie.
Thanks. Now that you know a little bit more about the research launching on today's mission, let's review a few quick facts about today's launch vehicle. The Falcon 9 is a two-stage-to-orbit rocket. It uses liquid oxygen, often referred to as LOX, and rocket-grade kerosene, known as RP-1, for its propellants. The Falcon 9 has 9 Merlin engines on the first stage and a single Merlin engine on the second stage to deliver a payload, in this case, the Cargo Dragon spacecraft, to the desired orbit. The SpaceX Falcon 9 rocket at the pad previously flew on the company's 11th cargo resupply mission to the station, and the Cargo Dragon is the same spacecraft that flew on the company's 6th resupply mission. Today, the Cargo Dragon is the only spacecraft that can return scientific research from the space station to the Earth. NASA's Amanda Griffin was able to sit down recently with Jan Clausen from Made in Space to learn more about a piece of hardware launching on today's mission.
Hi, I'm here with Jan from Made in Space, who's looking to revolutionize the fiber optics industry with space-enabled technology. So Jan, tell us a little bit about the experiment you have going up.
So the experiment is to process an exotic material known as Z-bland into fiber optic cable. The purpose being, in 1G, Z-bland creates little crystals inside of it that kind of ruins its performance as a long-range communications fiber. In 0G, the hope is that those crystals are diminished significantly so that then we can use it for, big, long cables to be used for the internet and all sorts of telecommunications roles.
So what exactly is Z-bland and how is that different from what's currently being used in fiber optic cables?
So current fiber optic cables are in general made of silica. Z-bland is a special material that's made of a whole bunch of different elements that is just more stable, the theory goes, in 0G.
Okay, so you say it's more stable in 0G, and then you're going to bring that down to Earth. And then what will you hope to happen to it when you implement it here on Earth with the new Z-bland?
Well, when we get it down to Earth, we'll take it for study, and we're hoping to see that the attenuation is a lot less than silica fibers. And the attenuation is how much light is lost when you shine a light through the fiber optic cable.
So for the average Joe, what would that mean to them?
So that'll mean, ideally, that we can replace current fiber optic cable with Z-bland cable. And that would result in shorter communications times, less delay in communications, more bandwidth for companies to play with, and hopefully overall a increase in the amount of fiber optic cable for your internet.
So you're trying to make life better here on Earth?
Yes.
It's excellent. And how long will you be up there making this?
The current plan in our prototype experiment is for a month. We'll manufacture hopefully 1,500 meters of fiber and bring it down and study it. And then hopefully use the results of that experiment to kind of fine-tune our process and then eventually create a commercial unit that can process kilometers of fiber. The ultimate goal is ultimately to produce hundreds of kilometers of fiber that we can then bring back to Earth and sell to the consumer.
Thanks so much and good luck with your experiment.
Thank you very much.
Back to you, Stephanie.
At T-minus 25 minutes and counting, let's go back to the control center for an update of today's launch.
Thank you, Stephanie. As you've been hearing, today's launch of SpaceX CRS-13 is a collaborative effort of scientists, but that's not all. Mike, can you tell us more?
Yeah, the 3 members of the International Space Station, Josh, are awaiting the arrival of Dragon on Sunday, and teams here on Earth are working hard today to make that special delivery to them. Adjacent to NASA's Kennedy Space Center at Cape Canaveral Air Force Station, the SpaceX Launch Control Center team is working with its partners, as you see here, at SpaceX Mission Control in Hawthorne, California. And meanwhile, in Houston, Texas, at the International Space Station Mission Control Center, teams are overseeing today's launch and awaiting the launch of Dragon and Falcon as the spacecraft then would head toward the International Space Station for arrival on Sunday. So as you can see, it is a total team effort spanning the U.S. from the east to the west coast. And at T-minus 25 minutes and counting, we'll send things back to Stephanie Martin now, and we'll keep our ears on the loops here and let you know how things are going, Stephanie.
Thank you, guys. SpaceX CRS-13 is an example of NASA's work with the American private sector to infuse innovation, advance technologies, and accomplish the nation's goal of human missions back to the moon, onto Mars, and beyond. NASA partnered with Orbital ATK and SpaceX under the first commercial resupply services contract to deliver cargo to the station. This approach provided a technical and financial boost to the U.S. industry to develop commercial space transportation capabilities. In this approach, NASA serves as a long-term customer, providing a market base for commercial launch services. In 2016, NASA selected Sierra Nevada Corporation's Dream Chaser spacecraft to serve as an additional cargo-carrying spacecraft. NASA has worked with the company on the Dream Chaser since 2010 as part of the agency's Commercial Crew Initiative to aid in the development and demonstration of safe, reliable, and cost-effective crew transportation capabilities. As you can see, they recently completed an approach and landing test over Edwards Air Force Base, which proved the spacecraft's atmospheric flight performance along with its return and landing capability. The Dream Chaser will begin delivering cargo to the International Space Station in 2019. These partnerships not only help NASA by providing access to the space station and allowing the agency to focus its resources on exploring beyond low Earth orbit, they also help our nation by strengthening the industrial base, developing a new high-tech industry, and expanding our economy. You've already heard about human health and fiber optic technology research. Another interesting experiment launching on today's mission will study how the Earth uses energy from the sun. This will help scientists better understand how our planet is evolving. Let's learn more.
Let's say this is the equivalent of the sun's total energy output. You can accumulate $100 a lot of different ways, but $100 is $100. If energy from the sun were $100, it would be important to know what kinds of currency was coming in. Big groups of pennies, whole dollar bills, or combinations. The total amount of solar energy falling on Earth generally doesn't vary more than about $1 to $100. But the kinds of energy from the sun can fluctuate. Remember that light we see with our eyes is actually a combination of many different colors or wavelengths. That's true also for the light we do not see. The composition of that light matters to understanding Earth's energy budget, and that's the reason NASA has a new instrument designed to study this question. It's called TSIS, the Total and Spectral Solar Irradiance Sensor.
It is important to know that the sun supplies virtually all of the energy coming to Earth. But in between the Earth and the sun, there is the atmosphere. And in the atmosphere, there are clouds, there are aerosols, that is particles, there are gases that interfere with the solar radiation reaching Earth. So that's why we need to fly a satellite to be above the atmosphere.
Mounted to the International Space Station, TSIS will collect detailed assessments of solar energy. Those data will be vital for scientists to make more accurate forecasts about climate change and other interactions between our planet and our parent star.
One of the risks with human spaceflight is the debris in low Earth orbit. Launching on today's mission is a piece of hardware that will measure the debris around the space station. NASA's Amanda Griffin has more.
I'm here with Joe Hamilton, and we're talking space debris. Joe, can you tell us in space around the ISS, like how much debris hits the space station on any given day?
Well, we don't know exactly. We have estimates of what the environment looks like, and there's no sensors that tell us when the space station is actually impacted by small debris.
And that's where you guys come in with your new space debris sensor, right?
Right.
Okay, can you tell us a little bit about that? Like, where's the space debris coming from first, and then how are you going to record that?
So the debris we'll be measuring comes from human activities in space. Okay. And we're going to be using multiple layers and multiple techniques to try to measure not just that the sensor is impacted, but how large the object is, what direction the impact came from, how fast it was going. And by measuring the energy of the collision, we also hope to be able to estimate the density of the object.
Okay, so you're measuring a lot of points there. So you mentioned how large the objects were. How small of objects can you measure with this sensor?
Well, the sensor should be able to pick up a tiny piece of, just a tiny grain of sand.
Why do we care about a tiny grain of sand in space?
Well, even something small can cause some damage when it collides at high velocity. Okay. It might hit, say, a handrail and cause a sharp edge that.
Oh, and then if an astronaut's glove runs against it.
Exactly.
Okay, so yeah, so that's important work that you're doing. So I understand your sensor will be on the space station for 2 years. What will your team do with all that data that you collect?
Well, the data that we collect will be used to gather statistics, and those statistics are used in the engineering model to update the environment estimates of how much debris is in each of the orbits in low Earth orbit.
And ultimately to help inform future spacecraft design, I assume?
Yes.
Excellent. Well, good luck with launch today, and we look forward to seeing what comes out of your data and how that can help us, delve further into the universe.
Thank you.
Thanks for being with us. Back to you, Stephanie.
The Center for the Advancement of Science in Space, known as CASIS, is the organization that manages and oversees research on the International Space Station U.S. National Laboratory. Recently, CASIS unveiled its latest mission patch, designed by Lucasfilm. It represents all of the payloads intended for the National Laboratory in 2017 and features characters and spaceships from the Star Wars franchise.
Growing up, I was always a huge fan of science and space, and if I wasn't in the film business designing for movies, I would hopefully be working for NASA.
There is a long, pronounced history with mission patches, both from the aviation industry as well as the aeronautics industry. Traditionally, for NASA-related patches, the astronauts themselves have been designing those patches for years. But at the ISS National Laboratory, we try to collaborate with unique partners to help develop these patches that are representative of all ISS National Lab research during a given calendar year. And who better to collaborate with than Lucasfilm?
In designing the patch, I had to bring in the best designers that I could think of, and that's Kelly and Stacy of Everly Design.
He asked us, hey, would you guys be interested in working on this project? And our eyes were just like, yes.
I actually first worked with them on early designs of the Rogue One title. It was a great opportunity for the three of us to work together again. The first step was to figure out, okay, what are the iconic moments or imagery that we want to merge with the space station?
In particular, there was this one scene on Tatooine. They have that beautiful sunset. We took elements of that and derived our colors for the final piece.
Doug's creative vision was to try to include some of the droids that have been involved in the Star Wars franchise in this mission patch.
And so the obvious choice was, okay, let's design it around the new robots like BB-8 and Chopper and K2.
And that is also very symbiotic of the ISS, because the ISS is all about enhancing technology.
That captured everything about the space program for me. It talked about the future, it talked about the adventure, the longing for the adventure.
Hello everyone, today we are going to watch the launch of a SpaceX Falcon 9 rocket, launching the also SpaceX built Dragon spacecraft CRS-13 to the International Space Station for resupplies and scientific payload. The Falcon 9 rocket is going to be reused again, and it has been reused before. In fact, this is SpaceX's most reused, most previously flown rocket today to launch. It will, however, not launch on a drone ship. It will launch back at Cape Canaveral, as the Dragon spacecraft only goes to low Earth orbit, and that leaves it with enough spare fuel to go all the way back to Cape Canaveral, which is of course easier and safer to land than on a drone ship. Now, looking at the map on the bottom left, I'm going to go right back to SpaceX now, but take a short look at that map. You can see that the ISS is already moving somewhat away from Cape Canaveral. However, the main priority for the launch windows to the ISS is that the orbital plane, the orbital inclination, lines up with Cape Canaveral, rather than that the space station is right over Cape Canaveral. This is because it takes relatively little fuel to make your orbit a little bit higher or a little bit lower, or really the spacecraft once launched is already in a lower orbit than the ISS and then has to boost its way up to the ISS. So in the beginning it's already going faster than the ISS, so it will catch up, and depending on how long you do that and when you boost it up, it's fairly easy to catch up to the ISS if you are behind or in front of the ISS. But if your orbital plane isn't aligned, it does necessarily take a lot of fuel to adjust your orbital plane. That's just a loss of physics and geometry. You can't do anything about that. Even if you have a lot of time, it does take a lot of fuel to adjust your orbital plane. So the orbital planes being aligned is a much higher priority for the launch window than catching up or falling behind the ISS, which is why at this time of the year or at this time of the month, the orbital mechanics will have to launch with the ISS basically on the opposite side of the planet.
right until it leaves the pad. We've also installed a new flame diverter system that can withstand much longer engine firings, which allows us to do more static fire testing here instead of shipping all of our reuse cores back to McGregor, Texas. Upgrades to the Strongback, which is the tower next to the rocket right here, also include new lift cylinders. You can see those new lift cylinders, they're the blue objects right here. These stronger lift cylinders allow us to do one continuous lift process from horizontal all the way to vertical, whereas before we were doing a two-step process. We've also completely upgraded the lock system on the pad. This allows us to do much faster densification and loading that LOX onto the rocket once it's dense. Overall, Slick 40 has been upgraded with additional redundancies to make it safe and reliable, as its LC-39A cousin to the north, which is helpful as SpaceX often sends employees and equipment between the two pads, so it's good to have as much commonality as possible between them. Together with Pad 39A and our West Coast launch site in Vandenberg, SpaceX now has 3 operational launch pads. More launch pads means more launches, which is the key to full and rapid reusability.
11 years ago, Dragon was just a design on a piece of paper. Today, it's the only vehicle flying that can deliver significant cargo both to and from the International Space Station, and it's been an exciting ride to get us to where we are. In 2010, SpaceX became the first private company to send a spacecraft to orbit and return it to Earth. 2 years later, in 2012, Dragon became the first privately developed spacecraft to visit the ISS. Since then, SpaceX has made a total of 12 trips to the ISS, and we're under contract with NASA for a total of 20 cargo resupply missions. We're currently flying cargo missions, but ultimately we will fly astronauts on crew missions, with our first crew demo mission slated for next year. Whether we're flying cargo or crew, our relationship with NASA is instrumental to mission progress and success. Today's mission marks the second time we've sent a previously flown Dragon to the ISS. The first time a Dragon was reused was on CRS 11 in April of this year. Today's spacecraft was flown for the first time on CRS 6 in April of 2015. That happens to be a mission that I remember quite well, as it was my first rocket launch as a SpaceX employee. Dragon has come a long way from just a design on a piece of paper, and we chatted with Dragon Mission Management Director Jessica Jensen to find out more about that journey as well as today's mission.
Hi, my name is Jessica Jensen. I'm the Director of Dragon Mission Management here at SpaceX. My group is the main
Hi, my name is Jessica Jensen. I'm the Director of Dragon Mission Management here at SpaceX. My group is the main interface the cargo on the vehicle, and 2 is meeting all of NASA's safety requirements. In our partnership with NASA, we have a contract for cargo resupply services to the space station. The first contract was set up for 12 missions, and we recently completed the 12th mission in September of this year. Then we have 8 more follow-on missions for this contract, and then after that, we jump onto the CRS 2 contract. And that is where we're going to be using the Crew Dragon vehicle to transport cargo to and from the space station. And the nice thing about that is the Crew Dragon vehicle has additional safety features beyond the vehicle we are currently flying, as well as a significant increase in capability of the type of research and science payloads we can fly. Dragon carries 2 types of cargo, unpressurized cargo and pressurized cargo. In the pressurized section of Dragon, we carry about 3,600 pounds of cargo. These are all items that are going to stay inside the ISS, primarily for the astronauts that are there. So these are things such as food and coffee, but all kinds of science experiments as well. For the unpressurized cargo, this is International Space Station hardware or payloads that are destined for use on the outside of the space station. Almost just as important as carrying cargo to the space station is safely bringing cargo back home. So the first thing we do when a Dragon gets home is unload all of the cargo and turn that over to NASA. After that, Dragon is shipped to the SpaceX facility in McGregor, Texas. In order to refly a Dragon capsule or a Falcon 9 first stage, several analyses, inspections, and tests have to be completed. And so it's one of the areas we do a significant amount of inspection and testing, and we also do it in coordination with NASA. NASA has been an amazing partner to SpaceX. We couldn't have done any of this without them. We look forward to carrying literally tons more cargo to the space station to keep the astronauts very busy.
As you just heard from Jessica, Dragon is packed full of supplies and science payloads for today's mission. Now, there are 2 main big external payloads in the trunk of the spacecraft. That's the lower section of the spacecraft right there. One of them is called the Total and Spectral Solar Irradiance Sensor, which measures the sun's solar energy flow to the Earth and how our atmosphere responds to it. And then also the Space Debris Sensor, which is a sensor that detects and measures the effects of tiny space junk particles that the ISS collides with during its trip around the Earth. Now, inside Dragon are dozens of other experiments, including technology demonstrators for cell science and fluid experiments, microgravity materials fabrication experiments, which attempt to manufacture polymers, crystals, and even fiber optics in space, and biology experiments, including plants, rodents, and even the behavior of astronauts themselves. There's even an experiment to grow barley in space, which will be the first step to an on-orbit brewery. Dragon serves a critical role not only in bringing these experiments up to the ISS, but also back down to the Earth for analysis once its mission is complete in just a few weeks from now.
We are at T-minus 5 minutes, and that means Falcon 9 is stepping into the final phases of terminal count.
The liquid oxygen load on both stages just completed.
Tanks pressing for strong bank
and
retract.
Falcon 9 is now performing its final checkouts to make sure that all of its primary systems will work in flight. Those checkouts include the communication systems and the avionics systems, all of which are looking totally nominal, just the way we like it. The engine chill began a few minutes ago at T-minus 7 minutes. That gets the engines cold enough to safely move propellant without causing it to accidentally boil. The next checkouts are the thrust vector control checkouts at T-minus 3 minutes, where we wiggle the engines to make sure they'll be able to properly steer Falcon 9 during ascent. Falcon 9 is going to enter startup mode at T-minus 1 minute, at which point it is in full control of the remainder of the countdown. Dragon, of course, also performing its own final checkouts to make sure all of its primary systems are going to be working in flight. Again, it's going to take a couple days to get to the space station. And just before liftoff, watch to see the strong back retract to give Falcon 9 a bit more clearance during launch. Currently, the range is a go. Everything weather-wise is still looking golden. And let's listen in to the last couple minutes of terminal count.
Stage 2 TVC motions complete. Stage 1 lock slope closed out. Stage 1 lock slope closed out. Vehicles transitioning to internal power. Stage 2 lock slope closed out.
So we are closing into the 1 minute to launch. I will then start the counter and just watch the launch itself. Again, this rocket is scheduled to land back at Cape Canaveral, not on a drone trip. And
AFTS is ready for launch.
Sonic boom as it approaches the landing pad. While at launch, unfortunately, you can't.
F9 is in startup.
LDs, go for launch.
Stage 2 pressing for flight.
T-minus 30 seconds and count.
Stage 1 pressing for flight.
T-minus 15. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. ignition, liftoff. Flight operations. There we go. Stage separation.
So we have stage separation, and as this happened relatively soon and relatively low compared to geostationary launches, and the weather is clear, we could see pretty spectacularly in the camera. And we're seeing the boost back burn now, so the first stage is now burning its engines to stop its own momentum and then head back to Cape Canaveral to land there. Here's a live view of the second stage engine, which is now still burning on to reach its actual destination orbit, and you could just see the fairing that was separated. As we actually left the atmosphere, there was no longer any need for aerodynamic shape or protection of the payload, so the fairing was dead as it was. The second stage kept accelerating and got behind the second stage, you can see it. On the left side we have a live stream from the first stage, which is firing its nitrogen RCS cold gas thrusters to turn around and vacuum. The grid fins now deploying, though at this point still relatively pointless because it hasn't entered the atmosphere yet, but as soon as it enters the atmosphere, these will help guide the rocket down to the landing pad to save on fuel for the reaction control system, which is currently turning the rocket around. Again, a common misconception, these are not air brakes, although they look a bit like air brakes, and they do of course slow the rocket down a little bit. They have aerodynamic surface area, they do have some slowing effect, but their main purpose is guiding the rocket as they have these holes and they're actually made of grid strings that are deeper than their wide, so really these work like a lot of aerodynamic fins or a lot of ailerons basically that are just next to each other. Falcon 9, of course, although it's not a winged vehicle, it does have some aerodynamic surface. It's a cylinder. It does prefer traveling along its axis. So you can use these fins to slightly turn it, and you can use that to make tiny corrections. So if you set it up precisely, you can use that to control your way down to the launch pad, to the landing pad, with relatively little fuel use. However, now the stage 1 entry burn is coming up, where it will burn a lot of fuel in order to slow itself down, so the re-entry doesn't get quite as hard as it would be from a straight drop.
Stage 1 entry for startup.
And you could just see the engine start, and of course rocket engines produce a lot of hot plasma, so that tends to make radio connections,
Stage 1 entry burn shut down.
high bitrate radio connections, a bit tricky, so the live stream tends to cut off there. But the rocket is actually relatively safe from that exhaust itself, because it is heading down at a high velocity, and
Stage 2 performance.
by definition, actually, it's really basic physics.
Stage 1
by the
ATS has
time
saved.
it has deaccelerated and is blown back up against the rocket, it has to have cooled down enough to the point where it's relatively safe already.
Stage 1 is transonic. Landing burn startup. Legs deployed. LZ1, the F9 has landed. Landing operators proceed to procedure 11.100, section 3 on LZ1 net.
And we have a successful landing with pretty spectacular live footage from the rocket and the pad. You did get to hear that triple sonic boom of the Falcon 9 quite a while after it went subsonic, actually shortly before the landing, because the microphone is quite a bit away from the landing zone, so the sound needs time to travel there.
OSM LDN countdown. Copy.
And you can now see the telemetry of the second stage getting faster and faster, and since this is a low Earth orbit flight,
Stage
it
2
will
and
just
terminal
go
guidance.
up to only
Second stage ATS has saved.
28,000 kilometers per hour, which is very soon when the second stage engine will cut off. For a geostationary transfer orbit, which is what the Falcon 9 is mostly used for, you would go all the way up to over 30,000 kilometers an hour.
Zico.
Since this is a low Earth orbit launch, it's now already done.
GNC confirms good orbit insertion.
With launch, it is. And we're now already close to
Acquisition
Dragon
signal near the
deploy.
loop.
No long coast phase, as this is again an ISS launch. Those go relatively quickly, as you don't have the long wait time of coasting up to geostationary orbit. And we have successful deployment. Wrong call. The next thing coming up is the solar array deployment, where the Dragon will deploy its own solar arrays to keep itself powered electrically until it arrives at the ISS.
Dragon's propulsion system has successfully primed and all thrusters report ready for firing.
And with that, the Dragon is on its way to head up under its own power to the International Space Station. It will now stay a little bit in that orbit. It will do a few minor corrections, but it will mostly stay in this lower orbit, which is due to Kepler's laws. Since it's a little bit lower than the ISS, it goes a little bit faster than the ISS, and so it will catch up to the ISS, which, as you can see in the map here, is pretty much on the opposite side of the planet, Cape Canaveral, of course, being at the southern USA, and not in the Indian Ocean. So it will keep in this lower orbit to catch up with that half orbit, and then boost itself up to the same altitude as the ISS to actually approach the ISS and dock, or rather go close to the ISS so the robotic arm at the ISS can capture it and then dock it to the ISS.
Expected loss of signal, Bermuda.
Which is the more modern and safe alternative to a classical docking. And we have successful solar array deployment, so Dragon is now fully powered, electrically speaking. However, it is about to pass over an area with little to no radio station coverage, so it's expected that we lose the live stream from the Dragon itself very soon.
Expected loss of signal, New Hampshire.
And with that, we have a successful mission for the Falcon 9. The Falcon 9 has ended its mission. Dragon is still on the way. In about 2 days, a little less than 2 days, 42 hours, so yeah, in roughly 2 days, the Dragon will arrive at the ISS, be captured by the robotic arm and then docked carefully. I will live stream that as well. Until then, I will live stream the 24/7 ISS stream, and I will show you a little replay of this launch and landing, and then leave the stream running for a few minutes for any questions, and then go back to the ISS stream.
7, 6, 5, 4, 3, 2, 1. And liftoff of the Falcon 9 rocket and Dragon spacecraft filled with science and supplies for humanity's research outpost in low Earth orbit, the International Space Station.
SpaceX ascent commentary will be...
I will later upload all the different viewpoints of this launch, as well as the post-launch news conference that NASA will hold after this.
1 minute, 50 seconds into the flight of Falcon, carrying Dragon toward the International Space Station.
You can see here the exhaust plume of the 8 outer engines spreading out, and then a little bit behind that actually the inner engine, the center engine, are spreading out as the atmospheric pressure is at that altitude lower
Standing
than
by
the,
for main engine cutoff.
sea level pressure that the engines are optimized for.
We have Miko.
And we have Miko, main engine cutoff. All 9 Falcon 9 engines have shut down as planned.
And the first and second stages have separated as planned.
7 seconds after separation, the second stage's single Merlin vacuum engine ignites to begin a 6.5 minute burn that brings Dragon into low Earth orbit. The engines produce 210,000 pounds of thrust.
That's 10, 9,
8, 7, 6, 5, 4, 3, 2, 1. And liftoff of the Falcon 9 rocket and Dragon spacecraft filled with science and supplies for humanity's research outpost in low Earth orbit, the International Space Station.
SpaceX ascent commentary will be performed by several people. The propulsion engineer calls out propulsion events. The avionics engineer calls out avionics health and Dragon separation. The range coordinator calls out Air Force satellite control network acquisition and loss of signal. And the ground station specialist calls out the SpaceX antenna acquisition and loss of signal.
At 1 minute 5 seconds after liftoff, Falcon 9 reaches transonic speed. The vehicle will pass through an area of maximum dynamic pressure, known as max Q, at 1 minute 18 seconds after liftoff. This is the point where mechanical stress on the rocket reaches its peak because of the rocket's velocity and resistance created by Earth's atmosphere.
Around 2 minutes 24 seconds into the flight, the 9 Merlin engines will sequentially shut down, and you'll hear the call Miko, which is main engine cutoff. This first stage will perform a boost back burn about 15 seconds later, heading back to nearby Cape Canaveral Air Force Station Landing Zone 1. We'll show you the landing on NASA TV about 8 minutes after launch, accompanied by the sonic boom just before landing.
Eight, 7, 6, 5, 4, 3, 2, 1. And liftoff of the Falcon 9 rocket and Dragon spacecraft filled with science and supplies for humanity's research outpost in low Earth orbit, the International Space Station.
SpaceX ascent commentary will be performed by several people. The propulsion engineer calls out propulsion events. The avionics engineer calls out avionics health and Dragon separation. The range coordinator calls out Air Force satellite control network acquisition and loss of signal. And the ground station specialist calls out the SpaceX antenna acquisition and loss of signal.
At 1 minute 5 seconds after liftoff, Falcon 9 reaches transonic speed.
The vehicle will pass through an area of maximum dynamic pressure, known as max Q, at 1 minute, 18 seconds after liftoff. This is the point where mechanical stress on the rocket reaches its peak because of the rocket's velocity and resistance created by Earth's atmosphere.
Around 2 minutes, 24 seconds into the flight, the 9 Merlin engines will sequentially shut down, and you'll hear the call MECO.
Nine, 8, 7, 6, 5, 4, 3, 2, 1. And the liftoff of the Falcon 9 rocket and Dragon spacecraft filled with science and supplies for humanity's research outpost in low Earth orbit, the International Space Station.
SpaceX ascent commentary will be performed by several people. The propulsion engineer calls out propulsion events. The avionics engineer calls out avionics health and Dragon separation. The range coordinator calls out Air Force satellite control network acquisition and loss of signal. And the ground station specialist calls out the SpaceX antenna acquisition and loss of signal.
At 1 minute, 5 seconds after liftoff, Falcon 9 reaches transonic speed. The vehicle will pass through an area of maximum dynamic pressure, known as max Q, at 1 minute, 18 seconds after liftoff. This is the point where mechanical stress on the rocket reaches its peak because of the rocket's velocity and resistance created by Earth's atmosphere.
Around 2 minutes, 24 seconds into the flight, the 9 Merlin engines will sequentially shut down, and you'll hear the call MECO, which is main engine cutoff. This first stage will perform a boost back burn about 15 seconds later, heading back to nearby Cape Canaveral Air Force Station Landing Zone 1. We'll show you the landing on NASA TV about 8 minutes after launch, accompanied by the sonic boom just before landing. And a sonic boom passes across the Florida Space Coast as the Falcon 9 first stage makes a pinpoint landing back at Landing Zone 1 at Cape Canaveral Air Force Station.
LZ1, the F9 has landed. Landing operators proceed to procedure 11.100, section 3 on LZ1net.
Meanwhile, in space, Stage 2 of the Falcon 9 continues to carry the Dragon spacecraft. Passes across the Florida Space Coast as the Falcon 9 first stage makes a pinpoint landing back at Landing Zone 1 at Cape Canaveral Air Force Station.
LZ1, the F9 has landed. Landing operators proceed to procedure 11.100, section 3 on LZ1net.
Meanwhile, in space, Stage 2 of the Falcon 9 continues to carry the Dragon spacecraft. Spacecraft separation. And Dragon is making its way away from the Falcon 9 second stage with the Earth limb in the background, headed toward its destiny and a rendezvous with the International Space Station on Sunday.
So with this I will close this live stream and be back with the ISS live stream in a few minutes. And as always, thanks for watching.